The loop is already a search. You have built it, in one form or another, in every video before this one. Across this series, one loop was assembled. Generate candidates, evaluate them with a shared harness, select the best, and repeat. That generate, evaluate, select loop is already an optimization, a search over candidate models driven by the score. One ingredient turns it into an evolutionary search. This video adds that ingredient and closes the arc. This assumes you are comfortable with a generate, evaluate, select loop, and with judging a candidate by a validation score. You might ask why an external loop is needed at all, now that a model can reason at length before it answers. For some problems, that deliberation is enough and worth trying first. But two things keep the loop irreducible. The evaluator is an external oracle. The truth of whether a candidate works comes from running it against the world, not from more thought. And searching a large, rugged space of structured artifacts is a different regime from one bounded pass. Here is the ground we cover. The evolutionary loop and its one new operator. Mutation, classical and knowledge-guided, the two spines converging, selection and collapse, fitness design, diversity, the lineage, and what you have built. Start with the definition. An agentic evolutionary framework is 5 things: a space of artifacts like expressions or programs, a fitness function that scores each, lower being better, a mutation operator that derives a variant from a survivor, a selection rule that keeps the best, and an initial population to start from. The loop runs like this. Each new generation is drawn from the union of 2 sets, the survivors of the current generation, the elite, and mutations of those survivors. Good structure is not discarded. It is carried forward and explored around. Draw the loop, and one node is new. An initial population seeds generate once. Then the steady cycle runs. Evaluate, select, mutate, and back to evaluate. And it is mutate, not generate, that takes the survivors as input, so each round's candidates depend on the last round's best. Mutation is the single node absent from the plain loop. Where do mutations come from? Classically, from blind edits to a tree. Genetic programming represents an expression as a tree and mutates it by operations on that tree. Subtree mutation replaces a random subtree with a new random one. Point mutation relabels a single node, an operator, or a variable. Crossover swaps subtrees between 2 parent expressions. These operations are blind. They propose a change without any regard for whether it improves fitness. Direction enters only later, through selection. That works when the space is smooth enough that random perturbations often help, but it leaves the proposal itself uninformed. A language model, as the mutation operator, changes that. Instead of a random tree edit, the model reads the current best expression, the data, and domain context, and proposes a specific, motivated variant. Here is a mutation prompt. The current best is x0 times e to the minus x1 with its score. The data looks like exponential decay, whose rate varies between samples. A retrieved note adds that decay rates in biology often follow Arrhenius kinetics, where the rate depends on temperature. Propose one mutation that might capture this. The model returns x0 times e to the minus x1 over x2, a temperature-scaled rate, a motivated variation a blind mutation would find only by chance. The model carries priors about which variations are meaningful, and domain context makes those priors specific. That is the edge over even a mature library like PySR, whose edits stay blind. Now, the moment the whole series has built toward, the quality of the mutator is set by the quality of its context, and that context is where the 2 spines converge. Evaluation becomes fitness. The harness that once scored methods now scores each candidate. And context engineering drives the mutator. The retrieval and context that once fed an agent now feed the proposal of the next variant. Follow one artifact through a single generation. The survivor x0 times e to the minus x1 enters carrying its harness score, error 0.0045, complexity 5, composite 0.0055. The loop selects it as an elite and passes it with that score and the retrieved note into the mutation prompt. The mutator returns the variant. The same harness scores it, error now 0.0021, composite 0.035. Because that is lower, selection keeps it, and the next prompt will carry its score in turn. No new machinery appears. One harness, one score, 2 roles. That is what evaluation becomes fitness means, concretely. Selection is what makes the search improve. Elitism carries the top few candidates from one generation to the next, unchanged, whatever the mutations produce. Without it, a bad round can accidentally lower the best score, a random regression. With it, the best score is monotonically non-increasing. It never gets worse. Two strategies choose who survives. Tournament selection draws a handful of candidates at random and keeps the best of them. The size of that draw tunes the pressure, larger for aggression, smaller to preserve diversity. Top K simply ranks everyone and keeps the best K. That is the simple default. But selection has a failure mode, and it is the most common one: population collapse. The population converges to a single candidate or a cluster of near-identical ones, and diversity dies. Diversity is the fuel of evolution. With nothing to vary on, the mutator spins on one form and the search stalls at a local optimum. This is the first thing to suspect when an evolutionary run does not beat the plain loop it started from. If the leaderboard does not improve, the population most likely collapsed early, and the mutator is circling one form without finding anything new. The fitness function deserves care because of what it now faces. In an evolutionary run, the harness is the target of a persistent, tireless optimizer. Every weakness in it is an attack surface, and a long run will find them. Two exploits are common: a trivially simple expression, a fitted constant, that scores well if the parsimony weight is set too high, and an expression that overfits by extreme complexity, a runaway polynomial, if the parsimony term does not scale. A well-designed weight blocks both. And a sharper hazard. A tool-enabled optimizer has been seen to recognize it is being evaluated, name likely benchmarks, and search out their answer keys. So run the fitness in a sandbox, with no route to the sealed data or the open web, and treat honest failure as part of the harness contract. If collapse is the disease, diversity is the cure. One remedy is islands. Run several independent populations in parallel, each exploring a different region. Every so often, let the best candidates migrate between islands, injecting fresh material. No single population can drag them all to the same local optimum. Underneath is the explore-exploit trade-off. Exploit means mutating the best survivors for small gains. Explore means proposing candidates far from the current population in search of new regions. Too much exploit converges early. Too much explore wastes budget. A practical rule: keep the population diverse, mix small mutations with occasional large jumps, and raise the exploration rate whenever the best score has not improved for several generations. This framework has a direct lineage worth knowing. FunSearch from DeepMind was an LLM-guided evolutionary search over programs, Python functions, scored by an automatic evaluator. It found better constructions for hard combinatorics problems and better packing heuristics. Its template is exactly ours: an artifact that is a function, a mutation that rewrites it guided by high-scoring past versions, a fitness that is an automatic evaluator, and a population sampled across many runs. AlphaEvolve scaled that template to evolve full algorithms and found improved matrix multiplication procedures and real data center scheduling gains, reaching results competitive with specialized research. And OpenEvolve is an open-source reimplementation, the hackable reference for the capstone, exposing the mutation operator, the fitness, and the population as parts you can modify. And the field is moving fast. Many new evolutionary frameworks now exist, so treat these three as anchors, not the whole map. One task has carried every example in this series, and it is worth naming: symbolic regression, discovering a mathematical expression that describes the relationship between features and a target. Unlike ordinary regression, the functional form is not fixed in advance. The search explores a large, discrete space of possible expressions. It is the teaching vehicle for 4 reasons. It is automatically evaluable, the fitness a number with no human in the loop. It is domain portable. A biologist finds enzyme kinetics, a physicist a force law, and the framework does not change. It is interpretable. The output a symbolic expression you can read and critique, and it has established baselines. Those baselines form a ladder, from linear regression through a plain pipeline and the classical library PySR, through retrieval-grounded and orchestrated agents, up to the evolutionary framework. Being comparable to each rung on an honest harness is the bar. One practical note before the close. Every mutation and every evaluation is an API call that costs money and time. Cost-adjusted fitness adds a term, the fitness plus a weight times the marginal cost of producing and evaluating that candidate. Using the marginal cost, not the run's total, is what lets it separate two equal quality candidates in favor of the cheaper one. But read it carefully. Cost is a property of the path that produced an artifact, not of the artifact itself. The same expression can be reached cheaply or expensively, so the cost-adjusted number scores a search policy, not a candidate. When quality and cost will not honestly collapse into one number, keep them apart and report a Pareto view: quality, complexity, dollars, and time. Step back one last time. The chapters of this series form a single argument. A researcher who can operate a rig, build a loop, engineer context, evaluate honestly, and orchestrate reliably has already assembled every component of an evolutionary search. The mutation operator of this video is the one part that was missing, and even it reuses the proposer, the harness, and the orchestration that came before. So the capstone is not a new topic. It is these components finally pointed at your own research problem, and the model they evolve is a model of your own data. The loop was always a search. You have built everything it needs. All that remains is to run it.